cone or a cylinder, a triangle, etc. Not that it's hard, but that's one of those sections. We got to look at all the different scenarios that they have for that. But before we do, I just wanted to wrap up section 6.2. This was the last thing we were doing, and this was volume by the washer method, right? But I just wanted to write this on the board. Isn't this what we determined in the end? That when we went around like some axis of revolution, we went around like the line x equals 2. Couldn't we just put the 2's there? And what if the line was like x equal to negative 2? Yeah, subtract negative 2. And then if it was going around the y-axis, we did this. We just made sure we wrote the functions in terms of y, right? So this right here, I just wanted to point out, I wanted to put this in their notes. I didn't write this on the board at the end. We kind of figured that out as we were working the problem, but it's just something you might want to keep and write down. So this is about which axis? That's about the x-axis. This right here would be about the y-axis. And again, I mean, it'd be a great idea. Let's just start class. Let's take two equations. We can use different ones from last class. I used x and x cubed. All right, let's do just some common functions we're familiar with. How about the square root of x? And we use x squared. And let's find the volume of revolving the region bounded by these two functions about the line x equals 3. Won't talk, but we'll set it up. We'll do the set. Let me set that up. Well, we always draw a picture first, right? Square root of x goes like that. Square root of x function curves like that. Y equals x squared, parabola, right? And eventually they do integrate. They do intersect. So there's that region we're talking about. We're talking about that region there. Find the volume of the solid that's generated by revolving this region about the line. Oh, and I wrote x equals 3. That would be, let's see. Somewhere over here, right? X equals 3, x-axis, y-axis. Okay. So if this is getting revolved like this, you all agree it's going to be dy, right? Because it's just like it's getting revolved around the y-axis. So that's when we're doing this dy. It gets revolved down to something like line equals y, right? Y equal to 3, or y equal to 2, or y equal to 5, or y equal to negative 5. Then it's getting revolved like this. That would be dx, just like the x-axis. So we're definitely going to apply this right here, true? All right. Well, to start out with, we need the limits of integration. We're going to find out where these two curves intersect each other. Let's find where they intersect. Now, some of you might know just staring at it. What does square root of x equal x squared? 0 and 1. That's where they intersect. Does everyone agree? Yeah. We can see at the origin that this value here, square root of 1 is equal to 1 squared. Of course, you could, square both sides. You get what? X and x to the 4th. You could solve that if you wanted. Square that, you get x. Square that, you get x to the 4th, and you can factor this. I think a lot of you realize you didn't even have to do that, did you? You still get the values what? 0 and 1. This is where these two graphs meet, right? So I'm going to start setting this problem up. They meet at x equal to 0 and x equals 1, but the a and b value, because I'm going around x equals 3, this is all going to be dy. So don't we need the y values? What's this y value? Right? 0 to 1? 0 to 1. I'm going to put my pi. Whoops. Squared. Squared. What's the function right here? Minus, what's this number? 3. Over here, minus a 3. The only thing left I have to do is rewrite these two equations. This was y equal to x squared, and this was y equal to the square root of x. I gotta write those such that I solve for x, right? That's the only thing we have to do. We're gonna put the outer here, right? And we'll put the inner here. So when we do that, we'll just look which one is further away from the axis of revolution and which one's closer.
X equals y squared.
Oh, good. Now, let's start with that one. Can you solve for x there? If y equals square root of x, what's x equal to?
Y squared.
X equals y squared. All right, got one. And that's further away from this, right? So x equals y squared, further away from the axis of revolution? All right. You're further away. You're the outer. Who's the inner? And when I need you to solve for x there, what would you get? Square root of 1. And there you go. But we were just going to set it up. Was everyone okay with that?
There's a question about, so your balance is 1 to 0. Is that your x value or your y value? Because they're, I mean, in this.
Outstanding question. They have to be in terms of this, they have to be y values because it's dy. But yeah, it was fortunate that this still came out to be what, 0, 1. A really good question. Because we're going around this, why we had to make sure everything was in terms of, dy, we had to find out what the value were.
But if it was an x function,
We would have used two x values. So I know I wrote a and b here, and when he has a really good question. I have a, b. He's saying these two numbers here are going to be y equal to some number, y equal to some number. These are going to be two x values. These will be x values, these will be y values. And it's where the two functions or two equations originally met, which I'll put there. Cool, everyone okay with that? All right, hey, in your notes, we're going to start now section 6.3. 6.3, this is another way to find volume. And goodness, not to make this all complicated, we already know a great technique, right? To find volumes of solids generated by revolving it around a certain axis. But there's certain functions or equations that isn't so pleasant. This isn't so wonderful. So we use another technique. All right, hey, can I erase that? I'll wait that one if I want. Some people I know like with the phone or something like that. I'll have it on video too. Is that okay? Yeah, I actually wanted just to finish with that. Because it's really a nice summary of what we're doing with the washing method. Which for all cases, right? What if it's around like the axis, the x-axis, y equals what number then? And the x-axis. This is a 0, right? I can erase. Hey, cool. So I'll wipe this out. That's 6.2. 6.3, still volume. This is volume by cylindrical shells. I wanted to give you a picture of a graph that we will start with. All right. This is y equal to x times sine of x cubed. And this graph just comes up like this. And then it goes like this, and it keeps going like this. But it intercepts here, everyone, on the x-axis. Some of you probably already know. Isn't the sine of pi equal to 0? You all agree sine of pi is 0? If you're curious what that number is right there. But it's being presented to you. I didn't want you to think you had to go and solve it right now. I know there's other times we'll have to do that. And since the sine of pi is 0, everyone, the cube of pi cubed would make this right here be what? Pi, and sine of pi is what? 0. I just want to point that out. This is the equation, y equal to x sine of x cubed. It keeps going. It keeps going. If you want to explore with technology, it comes down here and then it keeps going like this. Well, let's talk about taking the region bounded by this curve, all right? And the line y equals 0. So let's shade that right now. Can you shade the bounded region? And then I'm going to tell you which axis we'll revolve this around. Take the bounded region by y equals x sine of x cubed, that's that curve, and the line y equals 0. And this is y equals 0, right? So hey, let's shade here. So this is the bounded region. Let's find this. Let's find the volume of the bounded region. Well, I'll put solid generated. Find the volume of the solid that is generated by revolving that bounded region that we just mentioned about the y-axis. Okay. And this is just a good problem to present to give us an idea that, hey, maybe there's a better way to approach this problem than section 6.2. Maybe there's a better way than section 6.2 to approach this. Washer method. First of all, if we do the washer method, revolved around the y-axis, it would be very challenging to solve for what letter? X. Do you all agree? That would be one of the things we'd have to do. If we want to use the washer method, revolve this around the y-axis, then we know you solve for x in the equation at some point. And you notice that would be challenging? Second of all, if you look at this picture and you're thinking washer method, this would be weird how you did like outer minus inner. Isn't it the same function here? In terms of this getting revolved around here. But when we are going to roll this right around the y-axis, here I'll make sure this is nice and straight up and down. But we'll use a different technique. We're going to use a technique presented in section 6.3, the cylindrical shells method. Okay, so this is volume by cylindrical shells. So let's start out with just one cylindrical shell. All right, I'm going to take this piece of paper here. Here I'm going to cup it. I mean, that's a cylindrical shell right there, huh? That'll work. There's some cylindrical shell like this. It's a cylinder, right? And we'll just call this a shell. We're going to sum a bunch of these. And it won't be challenging to find the volume of that region, the solid of that's generated by revolving that region about the y-axis. But the first thing we have to do is use geometry and figure out, well, how do we get the surface area of some cylinder like this, of a cylindrical shell? How do we find the surface area of this? So, well, that forms a circle, right? What's the circumference of a circle? Brilliant, 2 pi r, is everyone agree? So we're forming actually right now, and we're just discovering, we're developing what? We're going from memory, if you recall. What is the surface area of some cylindrical shell like this? Well, the circumference would be 2 pi r here, right? But then I'd have to multiply the 2 pi r times the what? Height. The height. And everyone, that is it. That is the surface area of some shell. Well, I'm going to write that down. Let's put it over here. The surface area. I'm not talking about the top or bottom if we put lids, right? Just that lateral portion that we had would be 2 times pi times r. That was that circumference. And then I heard also times the what? Height. Times the height. Well, what we'll do is, let's think about here, I'm going to build one cylindrical shell. We're going to think about how we can just sum up an infinite amount of cylindrical shells to come up with the answer. And we do that by integral, right? Elongated s. So let's just look at one shell. When if this got revolved around the y-axis, it doesn't have to be perfect in your notes. What would it look like? So this would come what? Whoop, whoop. So this would just keep, it would reflect and do something like this, wouldn't it? Make sure that's not the way. All right, there we go. Something like this. come around here like that, and around here like that, around here like that, around here. Whoop, whoop, whoop. And we're revolving all this around the what? So have a nice big, just like that. So and we're going to build one cylindrical shell and focus on it. Okay? How about right here? That would reflect right here. Just like I had before. And it's just a shell like this. Okay? So I will put it like a little circle here just to say I know it'd be the top. This is one of the infinite amount of shells that we will sum up. So let's talk about the volume of that one cell, right? Well, the volume, oh, excuse me, not the volume of that, but just the area. And then we'll sum up the area of all these cylindrical shells. We'll sum up an infinite amount of cylindrical shells areas. What's the area of that one shell? All right, well, it would be, area would equal, let me put it down again, 2 times pi times radius times height, right? But let's write it in terms of this function. So when for the word radius, 2 pi, what are we going to put for the radius? We've got to look at this image carefully. All right. This is the curve y equal to x sine of x cubed. We know that. Does anybody know what I can call that radius? It should be something simple because it's coming from the origin out this distance along the x-axis. What letter? It's just x. Outstanding. So we're going to call the radius just the letter x. You say, are we always going to do that? Sure. If we're revolving around the y-axis. That'll be our radius of that shell. You all agree? From here, center out would be the distance x. But we need now something for the height. And we had 2 pi radius, that's x. Okay, you're x. What's the height then? What would be the height of this in terms of this equation? What's that height right there? Well, we need to know what that function is. What's the function? X times what? Sine of x cubed? And wouldn't that represent the height at any value of x? So for the height, I'm going to put the actual function of y. I mean, you could start with this. Let's start there. Keep it simple. Radius is x, height is y. Okay, but what can I substitute for the y? 2 pi x, and then this y gets substituted by the equation what? X times sine of x cubed. Cool. And what we can do is put an integral symbol now and say sum up all these cylindrical shells. One here, 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 and all the way down. I'll say let's go from A to B. 2 times pi times x times, just put the function in there, dx. This will be the formula if it's revolved around which axis?
Y.
The y-axis. So this is the first thing, and we'll write this down again for this problem. We discovered that, but be careful. This is different from washer method. In washer method, when it got revolved around the y-axis, we had everything in dy, right? True? By the cylindrical shells method, if you're revolving about the y-axis, everything is in terms of what letter? Dx. And then these values will be x values. These limits here will be x. I didn't want that to trick you, but that's what happens with cylindrical shells.
Can you pull 2 pi out to the front or not?
It's a great idea. I want someone to rewrite this. He goes, why don't you put the 2 and the pi out in front? And this will just be x times what? F of x dx. And then when just so you know, it's like sometimes you go, I'm going to have a hard time memorizing this. As long as you know this, you know that's that variable x, true? And then the height is just the what? The function, f of x. Radius was x, function was the height, h of x. So I can even draw some arrows here. This was the what? That was the radius, and this was the height. we're just summing a bunch of these shells. How many? An infinite amount. All the way from here, and then we're going to stop there. And we will accumulate all this to find the volume. Pretty cool method, huh? And this is helpful because the washer method would have been very, very challenging in this scenario. Hey, by the way, on that note, can you tell me what would be the formula that's revolved about the other axis, the x-axis? What's the formula? If it's revolved about the x-axis. All right? I think it's a good idea. Factor out the 2 pi. Put that out in front. A to B, what letter? Y. F of Y. And then lastly? And then we'll work this problem together. That would find the volume by cylindrical shells if that solid region you're talking about is going to be revolved about the x-axis. Just be careful, as I was saying, be careful, because wasn't this a little bit different from the washer method? Washer method is wonderful, it's outstanding, but there's a few instances like this example where it would be very challenging. And that's why we teach section 6.3. That's why I instruct. All right, well, let's work this problem together. Okay, I'm going to set it up. The limits of integration, everyone. This is getting revolved about the y-axis. I'm doing cylindrical shells, dx. I'll put the 2 pi out in front. Your suggestion, I like that. What's the limits? These were given. Can everyone see the x values? This was 0. And this was the cube root of pi. All right. If anybody wants to know what problem from the textbook this is like number 2 from section 6.3. It's like number 2. And the same thing, they drew a picture of the graph. All right, now what do I put down? Well, the radius. And I really do, I don't know about you, I just do this, I'm like, well, what's the surface area? 2 pi r times height. That's the radius. And the height is the function, which was what? X times sine of?
X cubed.
X cubed. Hey, be careful, this is just a warning. I've seen students do this on tests over the years. They're about to work the problem, and for some reason it slips their mind, they forget to put this x here. Isn't this automatic? They just think, oh, integral of f of x. It just slips. So if you ran that jam, you'll be looking at this going, man, I don't have an integral technique to do this. But now we have that x with the other function. There's a way we can solve this. We've all come from calculus 1. There's an integral technique. Very popular, allows us to solve this problem and other problems as well in our course. By the way, what is x times x? X squared. Sine of x cubed. And some people might just need a little, review of this. What's the method that allows us to integrate this? I heard it. What was it again? He calls it a U sub. It's the substitution rule. So when we got to find this integral right now, we're trying to find the antiderivative of x squared sine of x cubed. He says you have to use the substitution rule. He called it a U sub because a lot of times we just write U equals something. So I'm going to go off to the side here and perform a U sub so we can solve this. All right, so I'm going to do a U sub. Let U equal to, anybody know? X cubed. Brilliant. They went for the higher power. So if you need a little review on this, we looked at x squared, x cubed. You notice this was higher than this by 1 integer. And that's where they went for it. Not the sine of x cubed, just the simple x cubed. That's step 1. Step 2, differentiate both sides with respect to x. Okay, du. And this will be 3x squared dx. I'm going to do one more step, everyone, because my goal is to get rid of this x squared dx. So I'm going to divide that 3 on both sides. So I get 1/3 of a du equals x squared dx. And now it's time to substitute. Now I did this off to the side, right? And, there's people in this class, I know it, they're like, I can do that in my head. Like, they'll automatically do the U sub 3 steps in their head, and that's cool. But there's nothing wrong with us writing this down. True? Off to the side. Okay, let's start with this. What does this replace? All right, that x cubed gets replaced with a u, but the sin is going to stay, right? keep that SIN there, the sign. What replaces the x squared dx?
1/3.
The 1/3 du. So when I'm going to go up here and actually go in here with my chalk, say you're gone, but it gets replaced with a 1/3 du, right? You're like here, put in this, you're going to put a 1/3 and you're going to change this to a du. Now this looks all sloppy, so I'm going to clean this up, right? I got things crossed out and stuff. What do I have left right now? I have a 2 pi. I have a 1/3. Am I okay if I put the 1/3 with the 2 pi? I'm going to do that, isn't it? 1/3 times 2 pi over 3? Out in front of the integral? Still got this SIN left, and then what letters here? Boy, did this get nice. So does everyone see this? This is by the substitution method. And if you need in a class you're like, I need to brush up on that, oh, I can give you my videos, I can just give you some some supportive stuff just to get that fresh up on that, some practice problems.
So the 1/3, because it's a constant, we just took it out of the integral?
Yes,
Multiply.
because it was a constant. You could have left it there, but I was like, hey, we got another constant, might as well put it with the 2 pi out in front of the integral.
Because if we take the integral of constant, then it will be 1/3 x, and we would just be doing more work, right?
That's right. Now here's something else I want to point out. If you need a little review with U subs, I changed everything from x's to what letter?
Yes.
So do you notice, just being a math teacher, I didn't write these two same numbers down? Because these were actually what values? X values. These are now what values? They're U values. Now if you want to go find them, you can. You can figure out what they are. There's the little conversion. But I figure, how about just leave it blank. I'll finish this out and resubstitute, get everything back in x's, and then use these two numbers. That's what I did. Okay? But some students like to change those limits of integration to use. Ooh, anybody in here? I'm going to look. It's not the way he does it. There's about 2 in here. They actually like to do that. So if you're curious, you're like, well, how do you change this? Oh, it's right here. So that's an x value, and that's an x value. That's x, and that's x. What is 0 cubed? 0. What is the cube root of pi cubed? Pi. So if you want to know how to do it, it's not too hard, but you have to look at what you used in terms of what you set u equal to. Cool. But a lot of times I just leave these blank. Because I'm like, hey, I'll just keep going. I put everything in terms of x. I put it back in x, and I use the original limits of integration. All right, now, we were talking about this morning. Hey, what's the name?
No.
Oh, no. So here it is. Sometimes we get confused. The integral of a sine is a cosine, is a negative cosine. Just a mnemonic device. S. This way is derivatives, but this way is antiderivatives. This would be integrals. And it's just a mnemonic device that we can say, oh, I don't want to confuse a positive and negative. So the integral of sine is a negative cosine or cosine?
Negative cosine.
Negative cosine. Is that one great? Right there. What's the integral of an s? It turns into a negative c. This way is integrals. So the integral of sine is negative cosine. That helps. True? Because I know, it's probably happened before. You're like, oh man, I lost points. I put the integral of sine as cosine. Right? You're like, no, the derivative of sine of x is cosine of x. But the integral of sine of x is negative cosine. So I'm going to put that here. I'll put it with the 2 pi over 3. Almost done, everyone. I get cosine of u, and I put my 2 limits, right? Now, what are the 2 limits? 0 and what? Pi. If you didn't change them to u's, could I use the original x's?
No.
0 to pi. I would have just resubstituted. And right here, I would have had, what was u equal to?
X cubed.
And I put it back in. So you can use either one of these, and we put the proper limits. This was 0 to what? Cube root of pi. Which one do you want to use? I had about 2 hands show they like to do this. I'll be honest, most students do this, so they don't get confused. They just use the original what? Just remember, you got to resubstitute, true? So I'm going to use that just because I notice when I'm grading, most students like to do this.
Why did the 2 pi to the 3rd change to negative?
Oh, because of the integral of sine is a negative cosine, right?
Yeah.
And I just stuck it way in the front. But hey, we're fine volume. Do you agree our final answer should be positive?
Yeah.
Volume can't be negative, can it? So I do want to point out, I know that's negative, but watch what you get for your final answer. It should come out positive. You probably would have caught that. If you and I forgot that, we came down the end, probably got a negative answer and said, something's up. We'll look back to see what we messed up. All right, well, I'm going to use this one. What's negative 2 pi over 3 times, and all I'm going to do, everyone, I'm just going to do cosine of this minus cosine of that. Okay? What's the cosine of cubed root of pi cubed? That's a cosine of pi, right? Cool? And people know what that is? Then I would subtract, and I'd get the cosine of 0. Now, what's this number? Negative 1? What's this number? 1. What's the final answer? Oh, it's positive. What's a negative 2? Is that 4 pi over 3? Good job with this. Any questions on that? Step away. Yeah.
Gotta review these, the cosine
Oh, okay.
sheets.
Excellent. Doing a super job with this stuff. Hey, one more. I think it's always good to take a problem we did yesterday from 6.2 that we just found easier with the washer method, and let students try to approach it with the cylindrical shell method, just in case they wanted to do it, right? Like if you're wondering my preference, I like washer method, but you notice in this problem, it was what? It was just, this was way easier to deal with by using cylindrical shells. Nice. Hey, can I erase this? Yeah. Ooh. Great job with that, everyone. All right, I'm gonna pick something from yesterday. How about, or something very similar to yesterday. How about this? Y equals x. Nothing too crazy. And y equals x squared. And I was just wondering, maybe I should draw a bigger, since we're going to make these shells.
You're gonna make it a little bit bigger.
Throughout the year. Y equals x. Y equals x squared. And everyone, we're going to revolve this region right here, bounded by y equals x and y equals x squared, about the y-axis. Well, can we just start about the setup? If we use the washer method, let's see what we get. What will we do by the washer method? And we'll just set this thing up. X-axis, y-axis. This thing would go what? If we use the washer method, how would this go? Integral I dx or dy? See, when we can do a problem both ways, then you're a master. That's why I wanted to kind of finish up 6.3 with a problem like this. Let's set this problem up both ways. Washer method, going around the y-axis, the volume of the solid region, volume of the solid generated by revolving this region about the y-axis. Outstanding, you said dy. Okay, because we're using the washer method. And then, what's the setup? What goes here? Pi r squared minus pi r squared, right? And everyone, we will finish filling all this stuff in, okay? Don't worry, we will. I just want you to compare this to cylindrical shells. We're like, okay, cylindrical shells, what do we factor out in front instead of just a pi? 2 pi. But when it got revolved around the y-axis, what did we do? Dx. And here we just wrote the letter x. And then we put the function, right? Well, I'll just put a question mark here for now, because you and I might be kind of startled by this. How are we going to do that? Because how many functions you got? 2. So that's what we're talking about. Well, but let's start out with this. This, I think, to me, if you ask me, there might be a student in this class who prefers this. True, seriously. Me, I'm like, I like washer method. I think it's pretty easy. I just got to do outer minus the what? Outer minus inner, and I got to solve for what letter? X, right? Because it's going around dy. It's going around the y-axis. Which one's further away from the y-axis? X squared. Okay, so this one's further away. But you got to solve for what letter? So what would x equal to? Square root of y? Alright. Now, who is closer? The inner. But I need you to solve for x. What's x equal to? Oh, this was easy. It's just a what? Y. Where's Sean? Sean's theorem is, what if I had these mixed up? What could I do? Put what? Absolute value bars here, and I'd get it. And I never wrote down the limits of integration. These have to be y values, so what are these two y values? Pretty simple. What are they? 0, 1. Oh. Nice. How about this, though? I was wondering if you can help me. So let's build one shell. I think it helps when you just actually draw one of the shells. So I'm going here, and what would the reflection look like over here? The reflection would kind of come up like this. This would be underneath, right? There's the reflection. Good enough, right? Let's build one shell. On one shell, I'm like, okay, I go out like a distance x. Go up, stop. Come back over here, come up. I'm building one shell, and I'll get out of the way. I don't want to be a wall to anybody. Here, I just built one shell. So you can kind of look at it. The radius is still what letter? This is still the radius, everyone. Don't be fooled. The radius is still what? X. It's still X. Cool? So that's what? That's nice. You go, why? Can you see it? What's that distance from there to there? We can call that the distance X. True? What's the limits for the X values? Because these have to be X values. So where did these two meet? And X equal to 0, and what was this X value here? So this is 0 to 1. This is looking pretty easy too. Maybe the only challenge, but I know you're going to come up with this, is determining what to put for f of x. Recall, this really represented the what? Right? The height. And if you could look in there and figure out a mathematical way to come up with an equation for that little height right there, then you got this section, you're pretty powerful. You understand cylindrical shells. So I'm going to change this f of x and say, what do we put here? This is going to be the height part. Does anybody in the class have an idea? Someone's going to come up with this. Ooh, how could I represent the height? Because we're all confused. There's a y equals x, and there's a y equals x squared, but that would be the height there. What do you do?
X minus x squared.
He took the difference of the two y's. Do you all agree? Something similar to what we did with area. To find that little distance right there, which would be the height of that cylindrical shell, he says you just take the difference between this and this. That's what I'm going to call my height. X minus the x squared, and this would work too. Both of these are equivalent. Both, you can check, and we're not going to solve them now, but you can check both of these. Do all the math, you get the same mathematical answer. Cool.
So we wouldn't have to square the equation like we would in the Washer method?
That's right. And I know they can be confusing. That's probably why you'll find there's some colleges in Calc 2, they go, all right, let's just skip cylindrical shells. Students are going to get confused, you know. It's only great for certain circumstances. Washer methods are great everywhere, you know. But you're right, you got to be careful because we thought of what? Pi r squared minus pi r squared. We kept making all these washers. The thing with the cylindrical shell was, it was a bunch of areas. It was a bunch of 2 pi r h's. 2 pi r h's that we summed up. And so there's no squaring going on in terms of that, except when we know right now the function equation, that's it. But when both of these, you know, you can distribute that, solve it, you can square those, solve it, you get the math, they both the equivalent.
I want to test, do we get to choose, or like in the description is going to tell us to use which
Great question. For me, like, I usually let you choose, right? If I say, all right, I want you to do this one problem by the washer method, I'll be doing that just to assess that the students know how to do that. I do want to point out, that was a good question, because at least from section 6.3, you remember the problem previous to this? at least for me, I will definitely want to present a problem that's just like that scenario. And want to see, I'll say, what would be the most, what would be the best way to attack this problem? Because definitely washer method would be very challenging on that last scenario. Cool. So let me just repeat that, everyone, so you're curious. I do like to put a problem like that last one that I did. Previous to this, I had that what? It was just something that went up like this, it came out like this. We're like, man, with this, it was hard to solve for the letter X. Washer method would be very challenging, but by cylindrical shells, by that method, it would be not hard at all. We just had to do a substitution rule.
Can you just explain why the cylinder doesn't start on the x-axis?
Great question. So when we had to build all these shells to sum them up, because what we're going to do is we're going to have to, in the end, generate a three-dimensional solid. So if you start right here to make the first cylinder, I see that this curve is right here at the origin. So you're like, okay, I can't even move. But then you might, for your next one, you might put one right here. When I go for my radius, it's always going to be this outer curve that's furthest away. For the height, I'm always going to build like go up. But watch me keep shading this in. You're going to do that one, sum it with this one, then sum it with this one. I keep having to lift it up a little bit because I go straight out and then up. And I'll keep going, keep going, keep going. See, I keep lifting it up to get the, and then I build all these cylinders. I'd sum the areas of all these cylindrical shells. So that's what's happening there. So I know it can be confusing when there's two of them. But when you come to that radius, you go, let me just shoot out, here I'll build another one. Like, shoot out all the way just to see what would be the radius of that shell. Right? Then you'd be like, right? But still, I do want to point out, is the height all the way down? The height's only going to be the difference between this and this. So that's why I didn't shoot all the way down like before. So I wouldn't be doing that. You just like, this is going to be kind of height right in there. Just give them another shell when I wanted you to see that. I don't want to get too sloppy. But that's that height, the difference between them. The radius is just the distance x. I just want to label it. And this is just an x. But that height right there was height x minus x squared. Top minus bottom. Cool. Any questions on that? Excellent.
So, this method, the cylindrical shell method, so when you're revolving it around any arbitrary axis, are you just subtracting that from the radius?
That's exactly what you do. Very good. Very good. Any other questions before we go into section 6.4? Cool. Hey, section 6.4, it's a section we'll work on today. We'll even work on it tomorrow, just because all the scenarios change in each one. The title is just one word, it's work. And some of you who take physics, you might be very familiar with work. But the title of section 6.4 is work. Hey, does anybody know what work is? Force times something? I already heard it. Someone knows. The work is force times distance. Work is force times distance. The title 6.4. Work. Can't erase that. Work. Well, work is force times distance, right? If the force is constant. If the force is constant. The scenarios we're dealing with, everyone, is pumping water out of a swimming pool, right? Or some kind of cylindrical, it could be some kind of cylindrical tank that we're pumping water out of. Maybe a rectangular prism that's a tank. Maybe we're trying to pull a rope up the side of a building. And so the force acting on different parts of this very heavy rope is changing, right? It's varying. And so work equals force times distance. Sure. If this force is what? Just a constant force. I lift a book off the ground, everyone. The book weighs 10 pounds. It's a really heavy book. But I lift it off the ground, and you're like, well, that force is always going to be that 10 pounds, right? All right. force times distance. Then what's the formula if what we need in terms of calculus? If the force is changing, the force is varying. All right. So I'm going to start out with another notation. I think it's good to write it this way first. I'm going to have to take the limit of the summation of, I'll just use I equals 1 to n. Some force function, f of x, I'll say x of I, and I'll put a star here. You don't have to put the star. But I put x of I because we're going to think about breaking this up into just an infinite amount of small parts, whether if it's a rope or slices of water in a tank. And then I'm going to have to multiply it times the change in x. In terms of change in x would be the distance x. Okay, that'll work. F of x of I times change of x, infinite sum, right? Limit as n approaches what? Infinity. But that's one notation. What do we use? We use integrals, don't we? So I'm going to write this a little smoother. It's just the integral from a to b of f of x dx. Ah, that looks way better. That looks way better. True? I'm just saying this would be it. You know, and this is going to be work. So in front of all this, I'll just say, hey, this will find work. I'm just saying, you're going to notice though, when we build pictures, I don't care if you always think of it this way, but you'll notice we'll build a picture just to see what one little part would look like, and then we'll sum all of them up. Just like I made that one shell. Maybe I made a picture of just one shell. And as long as you see one shell, then you can think about it summing up all those shells. But we'll do the same thing with work. Okay? The only thing is, it's like, this is the kind of lesson, you know, you can do as much as you can in one day, but still continue it the next day. Because we're going to look at springs, you know, the work necessary to stretch a spring a certain distance, ropes being pulled up, water being pumped out of tanks, etc. Okay? Okay, so the first one I think we'll start with. Let's start with a spring. And by the way, I probably should write this. What if the force is constant? Work is just what? Force times distance, true? But I'm going to put the word constant. This is what's happening when your force is changing. All right, and when we're going to deal with springs, there is a law called Hooke's law. Does anybody know Hooke's law? Right? Well, I'll write the problem down, but to work with the problem with the springs, everyone, we do have to be familiar with Hooke's law. It's mentioned in the textbook in section 6.4. I'll gladly tell you Hooke's law that deals with springs. But the problem we're going to work, and when I want to do a problem like number 7 out of the textbook on page 450, so I'm going to do one like this. Number 7. Page 450, I mean this is in 6.4. What I'm do is change the, I think I'll change the force. I'm going to use force of 20 pounds. All right, here we go. Everyone, a force of 20 pounds. And LB, abbreviation for pounds, right? 20 pounds is required to hold a spring. Stretched 4 inches. Okay. Here. How much work is done in stretching it? From its natural length to 6 inches beyond its natural length. And if you didn't want to copy all this, you can just say, hey, he's doing a problem like number 7. I just changed, there's 10 pounds, I need 20 pounds. I did think it was important, I put all these words on the board so you know how to read this question, see exactly what we're trying to find. This does deal with the spring though, right? So when you're trying to find work done, as in this case, and when we definitely have to use Hooke's law. All right, well, what's Hooke's law? I'll read it to you, and then I'll write it on the board. We're going to have to work something off to the side before we start the problem. This is all we're going to do, right? That's the force function. But we need Hooke's law to figure out this force function. We got to figure out what's called the spring constant. So, you want to hear Hooke's law? All right, Hooke's law is the force applied to a spring is proportional to the distance that the spring is stretched beyond its natural length. I should say that again. This is just Hooke's law. Right? Hooke's law. The force applied to a spring, you see that letter K? That's called the spring constant, or the constant of proportion. Right? The force applied to a spring is proportional to the distance that the spring is stretched beyond its natural length. If you wanted to know what page it's on the book, I'll read it again. Just because you're like, what's Hooke's law again? Everyone, it's written on page 447 in our textbook. Hooke's law is mentioned. But we need to work the problem, or any problem in this section that deals with the spring. So say it again, you go, what's Hooke's law? The force applied to a spring is proportional to the distance that the spring is stretched beyond its natural length. So when we work this problem, or any problem in section 6.4 with springs, our first step is to find that spring constant, okay? I'm talking, let's not do an integral yet. Let's focus on that K. This spring constant, the constant of proportion, changes with different springs, right? There's thick springs, there's springs that aren't so thick, etc. So we gotta find that. So let's go over here, and what was the force they mentioned? 20 pounds, okay, 20 lb. I don't know K, but what was the distance that got stretched beyond its natural length? Right? Let's look. A force of 20 pounds is required to hold a spring stretched 4 inches. There it is. So I'm going to put the 4 inches here, right? Now here's what I encourage you to do. These problems, we're going to either write everything in either Newton meters or foot pounds. Let me say that again with work. All our work problems, our solutions, if we're in metric, we're going to put our answer in terms of Newton meters, which is actually joules. Did anybody know that? That Newton meters is actually joules? But if everything's in the US customer units, which is pounds and feet, we're going to put our answers in foot pounds. Well, that's not in feet, is it? So I highly recommend it. When we just start the problem, have everything in terms of feet. 4 inches, what is that in terms of foot?
Third.
Because there's 12 inches in a foot.
It's a third.
Is that a third of a foot? And I'm going to change it right now. I recommend doing it right at the beginning. This is 1/3 of a foot. Because in the end, we want to have everything in terms of foot pounds. If it was in the metric system, if they gave us stuff in meters, we'll get everything in the joules, which is Newton meters. All right. Anywhere else I have inches written on the board, I'll change it. Right there. Now let's change this. What would that be? 1/2 of a foot. Or you can put 0.5. I just recommend that. I know you're like, can I wait later, do that later? I'm like, I might forget. I think it's easier we'll get done right at the beginning. So for this x value, Hooke's law, 20 pounds, 20 lb, equals k times how many feet? 1/3 of a foot. What is k? And I need to walk and solve that. This is step 1 to deal with the spring problem. We're going to find k. What's the spring constant? 60. And I'll just go like that. We found the spring constant for this problem. For this spring. Because when I was this is like number 7. I bet you number 8 in the book, there's like 3 or 4 spring problems. You know, the spring constant is going to change from spring to spring, true? Cool. Hey, by the way, so what's my formula that applies to this spring? I can write it right now. It is now F equals what number? 60x. Cool. Question?
Is that the final answer?
No. Great question, though. I know it's funny. We did all that work. We're like, are we done? Because at some point, we're going to have to do an integral, aren't we? But we did something important. We have to do this with springs. We got to do this at the beginning. Especially with this problem. We had to determine the spring constant associated with the spring. But they have to give you information on that. right? They have to give you information.
Does the spring constant have any units? Is it
No,
just
it's unitless. Very good question. It's just a constant.
a-
It's just a number. Well, this has units pounds, this has units feet. Foot pounds is what we'll get for our final answer, but that K is just unitless, just a constant. But anyway, now, this is brilliant. We found the formula for f of x. What is f of x for this problem? 60x. We found this. That's my point. This problem's gonna be easy. Set up an integral, what's the force function? 60, that's your f of x. That's the force function. That's that spring function for this spring. dx, but now, what are these? Look at the question, read the next sentence. How far are we stretching beyond its natural length? Natural length is what value? 0, but how far beyond its natural length? 6 inches. Now I'm going to put that, is that right?
No,
Thank you, because I just didn't want you to make this mistake. Whoops. Wait, what is this now?
1/2.
1/2. Half a foot, right? So when we do all this math, our final answer will be in what units? Foot pounds. FTLBS, right? Or you can just put FTLB. Well, let's see what we get. Of all the integrals we've done today, this definitely looks like the easiest. Do you agree? But I had to do that off to the side. So hey, once we did that, we're almost done. Now we'll integrate this. What's 60 times integral 60x? X squared over 2, or 30x squared, I heard it. What's the limits? What's a half squared? A fourth? In my units? You can reduce this if you want to. FT dash LB. Or 15 over what? 15 over 2 reduced, FT LB. If you're a decimal person, that is 7.5 what? Foot pounds. That's the work necessary to stretch the spring that far. But we did have to use an integral to find that answer. Hey, great job. Just remember one thing. When it comes to dealing with the spring with work, the spring scenario, you definitely have to find the what first. The spring constant. And it's just something you do off to the side, right? And it's like, I gotta find that before I know what the force function is that I'm dealing with.
So are we saying natural length is 0?
Yes, natural length is 0.
Always?
Always. Natural length 0. So in this problem, they wrote this, look, natural length. And I do want to point out, remember Hooke's law? Hooke's law was, this distance right here was always beyond its natural length. So when you dealt with this, if they use wording in the word problem that's confusing, just go, wait a minute. Hooke's law, to find that constant, the force applied to the spring is always proportional to the distance stretched beyond its natural length. Well, that's super. That's the spring, right? We go, what's next? Well, let's look at like a rope. Okay? And when I'm gonna stick, let's put a rope on the side of a building. What's the weight of this rope they use?